Hello, everyone, and welcome to ACS Webinars, connecting you with the best and brightest minds in chemistry, live from Washington, D.C. I'm Mike David, and I will be your host for today's webinar, which is being co-produced with the Science History Institute as part of the Joseph Priestley Society series that promotes a deeper understanding of science, technology, and industry, with an emphasis on innovation and entrepreneurship. Our moderator for today is Bill Tuzinski, who is a partner at the Unami Group, offering sales and support and consultation in specialty chemicals and lubricants. Prior to that, he was a co-owner of Ivanhoe Industries, a specialty distributor, and has extensive experience in market and product development. Bill holds a PhD in organic chemistry from Cornell University and a BS in biochemistry from Manhattan College. But before I turn it over to Bill to introduce the event and speakers, let's hear from Miranda Bennett, the philanthropy manager at the Science History Institute, to tell us more about this free museum and library that collects, preserves, interprets, and shares the story behind the science.
Hi, everyone. So before we begin the webinar about recycling plastics, for some context, I think it's important to remember that our relationship with plastic has changed over time. So if you take a look at our website, which is sciencehistory.org, you'll find lots of resources that show the evolution of plastics and plastics recycling. So as you see in this slide here, there's a 1946 advertisement from the Hercules Powder Company, which is found in our digital collections. And in the ad, they really emphasize the durability, the toughness, the attractiveness of plastic. And that's quite a contrast from the throwaway culture of the 60s and from today's commitment to increasing plastics recycling. So I encourage you all to search our digital collections and website, where you'll find other stories behind the study of polymers and the development of the plastics industry. Most recently, we have the digital exhibit that you see on your screen here, which is on the history of AstroTurf since its introduction in the 1960s. And this history includes the opening of a turf recycling facility in rural Pennsylvania in 2022, which is relevant to some of our panelists today. So anyway, that's just a taste of what we have on our website, and I hope you'll come visit us or search the website for more context and history about today's webinar. So here is Bill Tuzinski to introduce our panelists.
Thank you, Miranda, and we welcome all of you. This is a wonderful audience. This is probably the biggest audience we've ever had, so we're very excited for this program. And we have some excellent speakers. You can see them there. And what we're going to do is we're going to start with Mimi Cooper and Caitlin Zikowski, who'll focus on the front end of collection and sorting. Then Henrik Dulinger will discuss physical recycling, and Jeff Carbeck will discuss chemical recycling technology. So with that, I will turn it over to Caitlin and Mimi, and I'll be back at the end for questions.
So, good afternoon, everybody. My name is Mimi Cooper, and I'm the recycling coordinator for Center County Recycling and Refuse Authority. And today I am joined by Caitlin Zikowski, and I had the pleasure of having Caitlin as an intern last summer. And she's currently a major at Penn State University, majoring in materials science and engineering. So our portion of today's talk is to bridge the gap between the science of plastics and their technical recyclability with the reality and challenges from the recycling collector and processor's vantage point. And then Caitlin's going to dive in further with plastics in more detail and maybe look at some solutions for the future, since her generation is the solution for the future. We're located in central Pennsylvania, and we're adjacent to the main campus of the Pennsylvania State University. Our county population is only around 160,000 people, and close to 98,000 of those residents live in a municipality that requires curbside recycling by state mandate. We operate a solid waste transfer station and a material recovery facility, or MRF, for processing recyclables. In addition, we provide most of the county recycling collection for residential, commercial, and a network of 60-plus drop-off locations. The Science History Institute asked us to touch a bit on the progression of recycling in the U.S., and Miranda alluded to this a bit. Recycling is by no means new. Frugal households have been doing it since the beginning of time, and with World War II, we saw an increase in demand for raw materials, which led to the beginning of recycling of durable goods for the war effort. Post-war consumption was on the rise in the 50s, and the increase of disposable goods in the 60s certainly set us on our path. The 70s then ushered in the environmental movement and spurred our nation into action. Landfills were reaching capacity, waste tipping fees were rising, and federal landfill standards were established through legislation. As such, states and communities looked for solutions to better manage their waste in a safe and effective manner. The late 80s and 90s saw many states enacting their own legislation regarding a broad array of disposal issues. In Pennsylvania, where we're located, the passing of Act 101 allowed for the collection of fees on the municipal solid waste tipping charges on each ton of trash, and those funded recycling programs through a series of grants. It also mandated the establishment of curbside recycling programs based on municipal population or population density. Such programs vary widely throughout the states in our country, and some don't have any at all. The evolution, dissolution of recycling programs, the advent of single-stream recycling, polymer advances, lack of program funding, corporate resistance to packaging, and extended producer responsibility, or EPR legislation, has led to challenges for those of us operating recycling programs today. One of the issues with recycling in the U.S. is that programs are bound by local parameters, and nationwide standards do not and cannot exist for a variety of reasons. Where you live, you may have no recycling, drop-off locations only, or access to curbside collection, and those collection types vary. Markets for those materials vary across the nation as well and can dictate what can and can't be recycled. Single-stream recycling, where recyclables are placed into a large cart and serviced by automated trucks, is perhaps the most convenient for the resident and the collector. However, it is not for the processor. It is the most contaminated source of recycling, with nationwide estimates of 25 to 35% contamination. Wish cycling of non-recyclable materials put in the cart and the downgrade of recyclable materials through compaction, such as broken glass shards mixing with paper fibers and intertwined containers that you can't break apart, contaminate recyclables that are going to the market. Dual steering collection separates paper fibers from mixed material containers, and it sits somewhere in the middle of curbside collection types. This does garner an improvement for the processor in terms of some less contamination, but could be seen as less convenient for the resident and the collector. Often, collection of the two streams occurs every other week, which can lead to more confusion by the homeowner. Collection itself may be fully automated or partially, which can still lead to increased contamination as everything is dumped curbside without any viewing, and compaction is still likely a factor with this type of collection. Center County Recycling and Refuse Authority operates a source-separated collection and processing facility, and this works on our smaller scale. At the curb, material is hand-sorted with any non-recyclable item left in the bin, with an explanation for immediate education to the resident or business owner. We have no compaction other than our commercially collected corrugated cardboard. Therefore, our materials are extremely clean and free from contamination. This allows us to find higher market value, and with respect to plastics, allows us to keep the various polymers separated, allowing us to capitalize on the higher value of some plastics. As you can see from our collection trucks, they are also source separated. Truck and trailer system on the left is used for residential collection, with cardboard and mixed paper fibers collected in the bed of the truck, and the other 6 compartments are for plastic, metal cans, and 3 separated colors of glass. This allows for easier separation at our processing facility and also allows us to get better market value for those materials. On the right is a commercial side load truck. This tips the 90-gallon trucks that are also source separated, but they are still visually inspected by our drivers. So if it's heavily contaminated, it is left at the curb with a note, and we have someone who actually goes out and works with the property owner to get that remedied. Again, keeping contamination from reaching our processing facility at the very outset. The bottom truck is for corrugated cardboard. This is the only material that sees compaction in our operation, and since it's fiber and source separated, it's not an issue. In our program, we are the collector and the processor, and we see the challenges that can affect both links in that recycling chain. We'll take a look at the issues that we encounter along the way, from collection to sortation and consumer confusion with the recycling arrows, and is it by shape or is it by number? And again, that is going to be regional. That can lead to contamination, packaging issues with the advent of multi-layer packaging, And of course, what's really driving most of this are markets. Is this material, despite being technically recyclable, is it getting recycled and turned into a new commodity? While source separation does lower contamination for us and it increases its markability, it does have its own limitations. With respect to the collection challenges, our curbside truck and trailer configuration has remained unchanged since the late 80s when we were mandated to collect collect recycling commercially. The material stream has also changed dramatically. A large increase in cardboard due to online shopping and a proliferation of plastic packaging has made our compartments very unbalanced. Various types of plastics and their market value has a large impact on what we can justifiably collect at the curb versus at drop offs. So, some of those lower value plastics, we can't really collect curbside. There's just no space for them in our current configuration. And the high volume of plastic materials, just in general, by their nature of shape, if not compacted, and the lightweighting of packaging also impacts the financial feasibility of collecting them curbside to allowing them to be recycled. Regarding challenges in plastic sortation, once at our facility, the plastic is further sorted into PET, HDPE natural, and HDPE colored from our curbside collections. As well, we also accept other lesser value plastic polymers from our drop offs and by arrangement for large scale items. For example, when Beaver Stadium was having a refit and we're looking at another one again, all their chair backs were brought here. We were able to find an outlet for that rigid plastic, but those obviously have to be brought in by special arrangement. However, other than PET and HDPE value, the value of other plastics can be relatively low. So we simply can't justify the curbside collection costs for these materials or the greenhouse gas emissions for the additional trucks that it would take to collect this voluminous material. And again, those limited markets allow us only to collect these at drop-offs. Depending on the polymer type, as I said, the value of a material varies widely. Natural HDPE last year and this year is currently around $1,000 a ton. And mixed plastics, such as the clamshells or the Starbucks cups right now, may only get us $20 a ton. So at the time, sortation costs may be offset the profit gained by strict sortation, and maybe just mixed bales makes more economic sense for the producer. Our material is hand sorted in a very labor intensive process, both at the curb and in our MRF. Changes in the material stream, as I said, the employment market, worker safety, job satisfaction have made exploring improvements a necessity for us. Caitlin will discuss a few of these a little bit when we're down the road, but we are embarking on adding an AI and air classification upgrade system to allow us to pivot more towards market demand. So when the plastics, those lower value plastics don't make sense to sort out, we would be able to pivot our sortation more quickly. However, this equipment runs such into the millions, even for our very small operations such as ours. The current piece that we're purchasing is $1.6 million. And this may be out of reach for many municipal or small commercial operations. Caitlin's now going to move on and discuss how this will allow us to better adapt to the market, packaging changes, and retool our workforce for other positions in our operations. So without further ado, Caitlin, I'm going to pass it over to you.
So a lot of the challenges that Mimi talked about are internal to our organization and our facility. But there's also so many challenges in the community, educating the community that we have here at Penn State that's constantly evolving, that numbering confusion that Mimi mentioned, how not every plastic is equal and not every plastic is always recyclable. And that leads to a lot of challenges in how do we educate this community? We see a lot of this consumer confusion contamination in event recycling, specifically Penn State football tailgates, which we'll see on the next slide. These Penn State football tailgates have a program called Blue Bags, where you can collect recyclables directly at your tailgate. All of these blue bags will get picked up and then brought to CCRA, which you see here in this big pile. It's a different sortation method, and it can push back production or processing at CCRA by many days. And ultimately, there is a large amount of contamination, about 50% contamination, due to how confusing it is to recycle, sometimes the state of the people that are at football tailgates, and other factors. So it's a huge challenge to figure out how we educate people properly on how to recycle in our specific community. And we're trying to look at further models in the future to pivot to higher, precise recycling. So not as much contamination. And we're going to try and see if we can implement new models at football tailgates in the future to help reduce that contamination rate. Another big thing that maybe touched on that kind of affects if something is recyclable versus actually recycled is local markets and global markets. So the price of material will fluctuate a lot in local markets, especially with plastics, and global restrictions can also affect these markets. So, for example, a few years ago, when China completely barred the import of plastics, there were a lot of these miscellaneous low value plastics just stranded on American soil with no solution. And then additionally, the cost of virgin materials can affect what kinds of plastics get recycled. So when petroleum is a high cost material, um, there's maybe a more likely chance that a plastic is going to get recycled because it costs less to recycle it than to make new virgin material. But if the cost of petroleum is low, it might be more economical to just make new virgin material, and that's typically what will happen. So diving into the different types of plastics, not every plastic is equal. PET, polyethylene terephthalate, and HDPE, natural high density polyethylene, are the two most widely recycled plastics in our country, with about 29% for both of them. So at CCRA, they come in and we kind of separate them by bottles versus jugs. And typically that gets us a good ratio of if it's number one or number two. But you can also use things like infrared spectroscopy to tell exactly what chemical composition it is. HDPE natural is high value compared to HDPE colored. And the reason for that is just because of the pigment that's in it. If you're trying to mechanically recycle HDPE and you have all these different pigments, it's hard to control the color, and that makes it a less desirable material and it lowers the value. Moving on to some more difficult to recycle plastics, but that still moves through CCRA. Plastic film, number 4, comes through with a few loads every year, and that usually gets turned into composite decking material. Mixed rigid plastics will come through like 1 or 2 loads a year, and miscellaneous plastics will also come through. But those are very low value because they're so mixed in composition. And then the really difficult to recycle plastics, number 3, polyvinyl chloride or PVC, is very difficult to recycle because when you are trying to mechanically recycle it or you're trying to implement heat in some way, it can degrade and produce hydrochloric gas, which is poisonous, very dangerous. So not a lot of people try to do that. Polystyrene, number 6 plastic, is for a different reason. It's very easily recyclable just as a material. But when you get into the economics of it, polystyrene, especially this expanded polystyrene, is really light. So if you're trying to load a truck with it, you can't get a lot of tonnage of polystyrene that's expanded on a truck. A lot of it's just air. And in the recycling industry, tonnage is equivalent to money. So polystyrene is really only economical to recycle when it's densified. And there's just not an infrastructure for that in the United States. And so that's one of the large reasons that polystyrene isn't recycled. And then again, number 7 plastics is just a mixed bag. So you have all these different compositions, and how can you get a high value product out of that if you don't separate them out? And it's so hard to separate with so many types of plastic. So what are we doing to try and solve this? On our small scale, we're trying to educate our community more and more through new tools such as Recycle Coach, which is an online app that can tell you what to do with your waste or recycling. We're trying to implement collection upgrades, like Mimi said, with those trucks. If we get different trucks that are more adaptable to changing markets, we can increase our efficiency. And then we're also trying to implement those processing upgrades, which will go hand in hand with our collection upgrades. So that would be AI sortation and being able to have that greater flexibility and material marketing with what comes through the line. On a large scale, what we need to work towards is implementing more legislation for packaging guidelines and extended producer responsibility, and also just informing producers how to design for recyclability. So avoiding those multi-material designs and things that you can't separate and can't recycle easily. And also choosing materials that are more likely to get recycled or more valued. So for example, maybe avoid putting pigment in your HDPE so that it's a higher value and more likely to get recycled. And then in the future, we're looking at a lot of alternative recycling methods. So chemical recycling, pyrolysis, they're happening, they're growing, and they're going to be talked about more later in this webinar. And then additionally, the development of new catalysts is always a great way to pursue different recycling methods that could be more economical in the future. So thank you for listening. And we are Center County Recycling and Refuse Authority.
Hello, everyone. My name is Hendrik Dullinger. I'm the VP of Business Development for EFS-plastics. EFS-plastics is a mechanical plastics recycler. We're headquartered in Listowel, Ontario, but we have another PCR facility in Lethbridge, Alberta, servicing the West Coast, and in the United States in Hazleton, Pennsylvania, where we do a lot of film processing. We divert over 100 million pounds a year from landfills. We have about 160 plus employees across North America, and about 350,000 square foot in shop floor across our facilities. This describes our process briefly. Again, in Hazleton, Pennsylvania, we are focusing on film materials, so commercial and curbside collected films, shredding and sortation of those, washing and grinding, and then produce an LDPE resin, whether that's a gray resin derived from more B-grade material, curbside materials, or a clear LDPE resin derived from commercial collection that goes then into film-to-film applications. In our sites in Listowel, Ontario, and Lethbridge, Alberta, we're focusing on 1 through 7 and 3 through 7 mixed rigid plastics. So some of the lower streams, we do believe that there's value in processing those mixed streams. It lowers the investments on the MRF side, and we are able, through processing on a large flake size, to recover more of these materials, including some of the number 7s that were mentioned in the presentation earlier, where we see that 70% of them are actually made out of polyethylene or polypropylene material. EFS also has the possibility to process black plastics through some of the sorting capabilities that we installed. So our spec is usually wider than those of the competitors in the market. Our end products are polypropylene, HDPE resins, and PET flakes, and we do custom color and compound those resins to fit various end markets. Everything we do is post-consumer, so we have a post-consumer certification through the Association of Plastic Recyclers, and that makes us compliant with many federal and state legislations that are being proposed or released right now throughout North America. Yeah, here you see our solution in the plastic waste hierarchy. This is something that has formed over the last year and a half, where the industry came together with all these technologies that are currently developing and said, okay, if we look at the life cycle of the products and the GHG emissions, what should we actually do when we look at plastic? So of course, on top is always source reduction and reuse. And then you go in the recycling, in the different recycling processes, and here you see mechanical recycling is still the best outlet if you look at the GHG reductions and the lowest overall environmental footprint. That being said, we believe that especially polyolefin materials should be funneled through mechanical recycling, but there's so many other plastic types out there and great technologies that are being developed. Some of those we will hear after my presentation. And we do embrace all these developments. We're actually looking at some of it ourselves. So while we believe first pass should be mechanical recycling, we embrace all the other technologies as well. What's currently happening with our resins? I know this webinar is called Past, Present, and Future of Plastic Circularity. So right now, the reality is really that a majority of the resins that are produced through mechanical recycling go into durable plastic goods. So piping, you see a composter on here, you see an umbrella stand, those roadside traffic pylons. So really durable plastic applications that incorporate post-consumer resins at high loads, like 80, 90, sometimes 100% in certain products. But yeah, the industry is developing different. There's a lot of consumer packaging companies that now want to see these products back on their shelves, and everyone is calling for packaging circularity. And the reality is also with the virgin prices on the resin side being so low, it's really difficult for PCR to compete in those type of durable plastic markets where a white spec virgin resin is really sufficient. So it puts a lot of pressure on the recycler, and so we're seeing a lot of investments in upgrading those type of mechanical recycled resins. So this slide then shows you more of the future of EFS in 2025 and beyond, which includes producing food-grade resins on the PET side. Again, we're focusing on 1 through 7, so we're getting everything from a PET thermoform tray to a PP yogurt cup in one bale, and a lot of food and non-food items. So we're currently working on a solution. How can those effectively separated between food and non-food, and make sure that the recyclable resins, which are at the end of the day number 1s, number 2s, 4s, and number 5s, then find a path also into food grade applications, or at least back into packaging, which is something you also see on the HDPE. While this HDPE detergent container here is not a food grade bottle, it will still be custom colored to go back into, let's say, a downy blue detergent bottle. On the low density material, the film material that you see on the very right, here is the goal to get into a high purity and high clarity LDPE resin to close the loop on film. So we're getting a lot of requests from product overwraps for PET, film over PET bottles, water bottles, those type of things. So our customers want to print on it. So it's important that this material is clear, and on the other hand, also free of gel. So your print doesn't, all of a sudden your baby face is not stretched on the diaper pack. Those type of things is what you have to keep in mind. Obviously, if you go into healthcare type of films, you need to meet certain toxicity level. So long story short, overall, with going into food and these difficult packaging applications, your quality needs to be getting better and better. And there's technologies developing from advanced wash lines to advanced extrusion to deodorization technologies that can meet those market requirements. Yeah, what's the driver of all of that? Ultimately, the consumer, Generation Y, Generation C, they're forcing a change. They hate plastics. Ask ChatGPT how many negative articles are per week globally about plastics. This is a wide range, but I mean, we see it all around us. Constantly, plastic is in the spotlight. And we know that plastic has some very good property, right? Especially when it comes to food protection, etc. A lot of times it has a better LCA than alternative materials. So, in our opinion, it's a waste management issue, not a material issue. And we want to make sure we stay on top of the legislation and continue educating legislator, but also the consumer about plastic recycling and what's already happening in the market. But the consumer obviously drives legislation. We're seeing a lot of extended producer responsibility. Since we operate on the Canadian side quite a bit, we're very much involved in the provincial regulations there that are hitting us this year and next. And we're also involved in the US with minimum recycled content mandates, whether that would be California, New Jersey, or Washington State. Those are really markets that are driving our business. And then on the other side, you have the voluntary brand commitments. That's very good as well. So there's the CPGs and their goals to reduce either virgin plastics or integrate PCR. That's sometimes, where one or the other might work. A lot of times it's lightweighting again, which was mentioned on the presentation as well. So if you lightweight and use less virgin material, then it might be difficult to integrate a higher load of PCR. So we're never navigating those type of words as well. But it's very fascinating business to be in, very challenging. And again, we're out there for 17 years trying to make it work. And I believe for the first time here in the last couple of years, we're really making a headwind, and I hope it will continue. So I really appreciate you tuning in today and listening to our presentation, and happy to answer your questions. Thank you.
Hello, everybody. I'm Jeff Carbag. I'm Vice President of Corporate Innovation and Care Solutions at Eastman Chemical. We're based in Eastern Tennessee, and here you can see the Smoky Mountains in autumn, which is the region we're very fortunate to be based in. What I'd like to talk a little bit about is an emerging technology called advanced molecular recycling, specifically focused on polyester materials. So I think this will be a nice build on a lot of what we've heard already around mechanical recycling, and we see this as a real complement to those technologies. And clearly, we need a variety of solutions to solve the total plastic waste crisis. Let me just say a little bit about Eastman. So we're over 100 years old. We used to be part of Eastman Kodak. In fact, in the 1920s, Kodak built the Eastman facility in Tennessee to address supply chain challenges related to the global war. And it started with methanol, and they grew into a whole host of chemicals and materials to support, at that time, the production of film and the development of film for Kodak. We're a company that's global today, over 14,000 people in over 100 countries. And Eastman, like many diversified specialty chemicals and materials companies, makes products that go into all sorts of things that you use every day, everything from textiles to coatings on drugs, ingredients for animal nutrition, for pharmaceuticals, for personal care. Plastics go into consumer products, automotive, really a very broad range of end markets. As a company, we made a very significant and serious commitment around sustainability, around really three basic pillars. So the first is the waste crisis, right? There's just certainly way more waste of a variety of materials in the world today than there should be. And we need to start to think about, as an industry and as a company, about how we start to use that waste as a feedstock. That's the area I'll focus on today. But we, of course, are also very focused on climate and on population growth, and how do we provide safe materials and chemicals to a growing population while addressing the challenges with climate change. Let's talk specifically about plastic waste. You've already heard some really great insights into some of the challenges and the problems, and some of the opportunities that there are here. And the way we look at it at Eastman is that ultimately this needs to be a feedstock for the chemicals and materials we make. But let's talk a little bit about kind of the magnitude of the problem. So if you think about the total global production of plastics annually, you're talking about 460 million metric tons. Number that's hard to really understand. But obviously it's a tremendous number. We start to think about how that material is handled. What we know, first of all, is half of it every year gets landfilled, put into bags, put into trucks, ultimately ending up buried in the ground where it essentially lasts indefinitely or for a very long time. 20% of it gets incinerated. That has mixed value. Of course, you get useful energy out of that, but it also produces CO2 emissions and potentially also emissions of other materials if you don't handle the output of that incineration properly. Even more of it ends up unintentionally leaked into the environment. This is where we see a lot of the challenges with the single-use plastics that end up in our oceans and streams and in our environment. And again, they persist for a very long time and can cause a range of problems. The issue with these is as they do break down over time, they produce microplastics. So we've heard a lot of concerns about that. Finally, of the total amount that's produced, and this is 2019 figures, numbers may be a little bit different, but I expect that the overall ratios are probably about the same. About 15% gets collected for mechanical recycling, but as you heard, that material has to get sorted and cleaned. And of that 15%, the total amount that actually does get mechanically recycled is around 9%. So again, numbers may have changed a little bit over the years, but I think the point being that the vast majority of the materials that are produced every year don't end up in a mechanical recycling stream. And so there are obviously opportunities to grow that mechanical recycling, and we fully support that. We believe mechanical recycling is the best option. But when that option isn't viable, then we need to start to find other ways to deal with plastic waste. And that's really what I want to talk about here in this presentation. So we've heard a bit about the process by which materials get mechanically recycled, plastics get mechanically recycled. One of the best, most easily and most efficiently recycled material are the clear PET water bottles. So just to use this as an example, those go and they get chopped and cleaned, get remelted, and then they can be molded into a range of articles. But we do know that over time that mechanical chopping and melting, thermal melting, ultimately does degrade the material. And so at some point, these materials are no longer fit for use, and they end up in the landfill. So if we think about how chemical recycling or molecular recycling is different, the key difference is that we take mixed plastic waste and we break it down into its constituent molecules or monomers, as they're called. And here, those monomers that they're broken down to then can be reintroduced into a polymerization process that remakes materials or makes new materials that essentially have the identical properties to the original material that the monomers came from. And in fact, you can even take those monomers or those molecular building blocks and do further chemistry to them and actually increase the value and the performance of the materials that you make. So you can take relatively low grade mixed waste plastic and actually produce higher value, more durable articles. And that's really what we're focused on at Eastman. Now, what I should say is this is a simple cartoon to explain the process, but to be very clear, each plastic would need to have its own type of chemical recycling process, and not all plastics can be broken down in this specific way. So we focus on polyesters. You've heard a lot about PET. That's a polyester. These materials have the advantage that essentially their chemistry can run forwards to make plastics, and using Le Chatelier's principle remember that from your chemistry classes, that you can run that reaction backwards and recover the original materials, those monomers that made those plastics. And so that's what we're really focused on at Eastman, is specifically molecular recycling of polyester materials, but it's an approach that works for other plastics as well. So why do we do this at Eastman? So first of all, we have a long history in polyester materials. We first started making polyesters to replace cellulose acetate film, and that's another whole Eastman sustainability story I don't have time to talk about today, about how biodegradable and compostable materials made out of cellulose acetate. In fact, the first slide we saw today had cellulose acetate on it from the 40s. But in the 50s, we started to replace the cellulose acetate films with polyester. And soon after that, we started to make polyester fiber, and we were deeply involved in making polyester fiber and fabrics and dyes. And that was a big part of the Eastman business that extended beyond Kodak. In the 70s, we got into developing PET for bottles. So we were one of the earlier developers and manufacturers of PET in North America for bottles. We then took that material and slowly over the years expanded its performance. So in 2007, we released Triton. If you go and buy a plastic water bottle or a baby bottle, or a blender that's got a plastic container, those materials are almost all now made out of Triton. Basically, that material replaced polycarbonate because of the fact that it didn't contain BPA. It still had that same toughness, durability, transparency. And so now there are many, many applications where this highly durable BPA-free material called Triton is available. And that is also copolyester. And then more recently, we developed TetraShield, which is a high-performance resin coating for automotive and other packaging applications like food. So we have a long history of making innovative materials out of these basic building blocks that I'll be talking about in terms of molecular recycling. And we also have a history of doing molecular recycling. So in 1976, as part of Kodak, we developed a high-pressure methanolysis process that took the X-ray films that you see in the lower right-hand corner and depolymerized them. And at that time, it was actually not to recover the monomers of the plastic, but it was actually to recover the silver that was used in the development of those X-rays. So going back to 1976, about the same time we developed some of these higher performing polyester materials, we were already starting to develop the technology to run the chemistry backwards and recover the feedstocks. In the 1990s, we developed a low pressure methanolysis process. So increased our capacity, and because it was low pressure, ran much more safely. In 1994, as Kodak was essentially going out of business, Eastman Chemical Company spun off as a standalone public company. And from the late or mid 90s to the early 2000s, we used to continue to run a low pressure methanolysis process to produce the feedstocks for PET, DMT, and EG. So there's a long history here of doing this chemistry, but at relatively modest scale. And what's different and what's new today is both the feedstocks we're using now to do this molecular recycling and the scale at which it's being done. So what are we doing? I think it should be pretty clear now. If we put the pieces together, we start with polyester materials that are hard to recycle, and we use those as a feedstock. We actually had to build 2 plants. So the first plant we built was a mechanical purifying process where we essentially process these mixed waste plastics into various streams that we can then feed into our depolymerization plant. The depolymerization plant breaks those polyester materials down into their constituent monomers. And then a third primary process is the purification and recovery of those monomers. So we can recover them at a level of purification or purity. It's essentially the same as you would get if you made them from virgin fossil fuels. Those then feed directly into our existing polymer production lines. So we can feed them right into our existing plants. They may be combined with monomers from virgin material as well, or from virgin feedstocks as well. And then in the end, what we get are these durable products that actually have much higher value. So we're actually upscaling the materials through this process. And we use a process known as mass balance. It's an ISCC certified process where we can account for every monomer comes into our plant, ultimately ending up in these products. So we can certify them as containing recycled content of a certain level using that mass balance process. So what you see on the left is a typical collection of materials. So you can see these are not clear PET water bottles. These are all sorts of other materials that otherwise would probably end up in a landfill or very difficult to recycle for a lot of the reasons that we've heard before. And through our polyester recycling technology, recover the monomers, extract out the dyes and the other undesirable organic components, purify the monomers, and then again, make these new specialty plastics and fibers. So if you think about it, on the left is a traditional way of making these kinds of plastics. But you start with crude oil that's extracted from the ground, and there are 10 steps to refine, convert, and produce the monomers. It would then ultimately be polymerized into the final polymer product. So essentially what we're doing is we're replacing that extraction process, the refining, conversion, and monomer production with just the last step. Recover the monomers, and then we go ahead and we repolymerize them into a new material. We can do that at about 90% yield. So fairly high yield, and the output of the materials is very high quality. So as I said, we see this as a complement to mechanical recycling. Mechanical recycling has by far the best greenhouse gas emissions footprint, and it uses existing infrastructure, and we're already creating lots of solutions using that process. And so we're in no way competing with that. What we want to do though is work with the harder to recycle materials where mechanical recycling isn't always an option. And what we want to do is focus on the quality of the material that we make, and ultimately the materials or the products that are made from those materials. We want to make sure that we really can essentially go through an infinite number of loops at that 90% conversion rate, because we're not downgrading the material, because we're taking it back to its basic molecular building block. So here's actually some pictures of actual materials in our mixed plastics processing. So what you can see is we take colored rejects from mechanical recyclers, the kinds of things that we've heard from others get sorted out. There's also purge. from those mechanical reclaimers. So there's melted material that can't be used. There's green bottles. So there's a lot of green bottles out there. And unfortunately, because of the green dye, they're not always compatible with mechanical recycling, where the focus is on clear materials. Carpet fiber. We take pre-consumer carpet fiber. So this is textile waste that's generated in the manufacturing process. We can run that in our process, as well as textile purge. So this is dyed polyester fiber. It has all sorts of different colors in it that we can extract in the front end part of our process. And finally, green strapping. So a lot of this is used to hold boxes and other items together in pallets. It gets collected and can't be recycled using mechanical processes. So these are the materials we're focused on now, and we're always working to expand the types of materials that go through our process. So where are we? So we've built our first molecular recycling facility in Kingsport, Tennessee, where our company's headquartered. As you can see, its nameplate capacity is about 110,000 metric tons of plastic waste annually, converted into monomer for making copolyesters and PET at 9% efficiency. And that plant went online March of last year, and it's now making very high quality materials. And we're selling materials in the market today that have what we call recycled content in it, based on molecular recycling. Our next plant will be in Longview, Texas, which is our second largest facility, and that's expected to be online in 2028. And we've also been working with the French government to establish a plant in Port-Jérôme, Normandy, France, where we'll again process about 110,000 tons annually to help support local and regional recycling efforts. So as you can see, there's an ongoing set of efforts to grow these capabilities. But we do have our first plant up and running. It's really exciting to see this kind of technology being practiced at scale and actually making new material with value in the market because of its recycled content. So as others have talked about, what we're really here about and focused on is how do we transition from a linear economy to a circular economy. There's lots of ways to do this, but hopefully what you see is that the advanced molecular recycling process is one new exciting technology that helps enable this with certain plastics that are hard to recycle otherwise. And, I think where we as an industry are going is we need to really think about this circular advanced recycling as a much broader capability, where we're really going to need to have this sort of take back and reuse mentality for many or most of the products that we make. So I think this is just the beginning, but excited to share this with you and eager to hear some of your questions.
I want to thank all our presenters for wonderful presentations, very informative, very insightful. And I'm going to try and get through as many questions as possible. If I don't get to yours, don't feel insulted. There are just far too many for the time we have. So I'll start off with Caitlin. And this question must be someone from Ohio State wanting to be like Penn State. And the question is, what would be the steps to try and implement the blue bag practice on other college campuses?
Yeah, so I think the first thing that you probably would have to look at is how your specific waste and recycling stream works, specifically in that university and in that community. You might have like a single stream, or we have a separate stream here. Every community is unique. So you have to take into account like those considerations, like can you send bagged recyclables or not? A lot of places don't take bagged recyclables if they're single stream or like an automated material recovery facility. That is a big consideration. Another thing, if there's trouble like getting the program off the ground, is evaluate if it would save money in any way. So if you would save money, like because you're not sending that waste to the landfill, you don't have to pay that fee. That would be a great way to try and get it off the ground and promote that it's a great sustainable practice to try and take on. So good luck with that.
I'll flip this over to Jeff because he just was the most recent speaker. And it's really a couple of questions I'm going to try and combine. And they relate to the economics of recycled PET versus virgin. Also on the quality of recycled versus virgin, And how do the energy consumptions and greenhouse gas production compare between the two?
Yeah, all great questions, and I think some of my co-presenters can probably answer some of that even better. But I'll start. Um, one of the challenges today around recycled PET is there is excess PET capacity globally, and so right now the price of virgin material is fairly low, and that together with a strong supply of feedstocks for mechanical recycling is putting a lot of pressure on the economics. And so, one of the things that we think will help drive some change there are some of these EPRs, these extended producer responsibilities that will kind of level the playing field a little bit and bring the economics more in line with the actual issues and challenges. And certainly, Mimi and Caitlin can talk, I'm sure, much more thoughtfully about that than I can. The only other thing I would add is that what we're trying to do, certainly in Kingsport, where we've for a long time made sort of higher value copolyesters. So these are more durable materials. They're not necessarily used in single use. To make the economics work, we're essentially taking the PET, the lower cost PET material, extracting the monomers out of it and using that as feedstocks to make higher value materials while taking credit for the consumer recycling. So it's a challenge to make the economics work. The other piece I'll just say very quickly is it's also about forming partnerships. So we've formed partnerships with large companies like Pepsi, for example, where we can put in place relationships where we can solve some of their challenges with their packaging needs and work with them to take back materials. And so, it's not just about technology and infrastructure. It's also about, if we really want to have a circular solution, companies around the circle getting together and figuring out how to share the value to overcome some of those challenges. Yeah.
Over to Hendrik now. There are several questions regarding contamination and how you handle it. One, some concerns with things like food contamination and packaging materials. And the other is, how do you work with the additives and colorants and other materials used in compounded into plastics when you're dealing with mixed stream?
Right, absolutely. It's a good question, and it's very challenging, right? Especially with the demand that some of our newer applications have. So when you go into a scenario where you want to reach circularity on packaging, thin wall, etc., low tolerance for gel and any discoloration. So you see a lot of mechanical recyclers that are taking this route, making larger investments on the sortation side. So whether it's AI sortation on the front end, several optical sorters with near infrared color sorting technologies. Then, of course, your wash line plays a crucial role. Are you cold washing, hot washing? Are you using some type of chemical wash to get more contamination off? Your extruder plays a big role. Is it a twin screw extruder where you have some type of better compounding of material, or is it your typical single screw that is used in mechanical recycling for a long time? And a lot of companies are also adding post sort. So even after it's washed, you have a flake sort again. So again, that adds to the cost of our process. I think Jeff was touching on that a little bit as well, how difficult it is to compete with a giant virgin industry. But I'm also seeing, just to echo what Jeff said, we're seeing a premium of 20 to 40% depending on the PCR for those companies that are really progressive and that want to embrace PCR products to make our equation work at the end of the day.
Mimi, this is for you. What is your opinion of mail-back programs and programs like TerraCycle? In European countries, stores have recycling bins for things like disposable razors, toothpaste, toothbrushes, etc. How economical is that?
Well, one, I did live in Europe for a long time. I lived in London and Vienna and was very familiar with TerraCycle there and familiar with it here. And I do want to start off by saying I think there is room at the table for absolutely everyone. But and it all works differently depending, again, where you are, your regional mandates, what you're bound by in your local markets. So TerraCycle, if they do one thing well, it's they get it into the minds of children in school to be responsible for your own waste. It's not just, I'm going to put it here and it goes away. You go home, you tell your mom, I can save my toothbrush, I can do it. Now, whether or not it is, in my mind, truly recyclable, a lot of those products are turned from waste into waste to energy facilities. So that begs the question, is that recycling? I can't answer that for each and every one of you. I know how I feel about it, but I do feel the value in it for teaching people that waste is our own individual issue as well as our community's issue, as well as a global issue, has value. So as far as the economics, he's been doing that company for a very long time. I'm sure if it weren't economically feasible, he wouldn't keep doing it.
If you're the recycling PET is really condensation polymer that you're recycling. How does that compare to, say, addition polymers?
Yeah, I mean, we're taking
something like polyolefins.
Yeah, right. I mean, the challenge is that it's very difficult to run a sort of a free radical polymerization backwards. And so, those materials tend to end up, if you want to do this kind of advanced recycling, they end up in a pyrolysis process, which is quite different from molecular recycling that we practice. The beauty of the condensation polymerization is essentially you have two molecules coming together, reacting to form the chain, and when they react, they release a molecule, in this case, methanol. So if you just put a lot of methanol into the polymer, you drive that reaction backwards in a very controlled way. And so there are lots of other condensation polymers that can be done in this way. So the reaction can be much more controlled and be run in a way that really recovers monomer that essentially you started with. So there are lots of different ways of thinking about recovering value from materials. We've heard about incineration, we've heard about waste to energy, pyrolysis, and then there's this what we call molecular chemical recycling, which is true reversible chemistry. But you have to look at each material and decide what's the best route.
Kind of a general question for everybody is, we're starting to see now with all the phones and computers and the growth of all of that piece, engineering thermoplastics starting to show up in waste streams. Is there any hope of those being potentially recyclable, or are they out of reach at present technology?
Well, from the mechanical recycling end, I think it's difficult given that there's a lot of flame retardants in there. I know that there's been some sorting technologies that are being developed maybe to better sort that material, but I don't think they're going to be suited for any type of mechanical process. Maybe Jeff, in your world there's a solution to it, but yeah, that's where I stand.
So maybe grind them into asphalt is about as far as they could go. Caitlin, question for you. Leaving non-recyclable at curbside, the option of hand sorting curbside sounds terribly time-consuming and inefficient. How does that work?
For us in Center County, it works well because we're on a smaller scale. And that's kind of how our system is. It's more personable than something. It probably wouldn't be able to exist in like an urban environment where you have so many people. But here, it's great in that it helps inform the consumer and the community member about what is and isn't recyclable. And it helps people kind of be more involved in that and keep them in on that conversation rather than having like a less personable system. So it has its cons. Obviously, it's more time consuming. But in the end, it helps us to get a higher purity stream. And that's what we're looking for. So it works for our community, but maybe not every community.
And as I alluded, the cost for making a single stream facility can run into $30 to $50 million. The throughput of material that we have for our location can't justify that. And our residents are so well trained at this point. What goes in the bin, we very rarely have to use that. So we did a single stream study about 10 years ago, and it simply did not make sense. I mean, we have a 95% participation rate, due to the fact probably that we're in a university town. We know we're in a bubble, but it does work for us. But it won't work everywhere. You have to be realistic with that.
Yeah. To add to that from a processor perspective, again, we process 1 through 7 plastics, so we're just looking for a clean negative sort. So if you have the capability, invest in that optical sorter for plastic and have them take all non-plastic contaminants out there. If you have a hand sorter on that, at least make sure they pick the bowling balls and the baseball bats and all those type of things out. We can handle the rest that doesn't break our shredders.
I guess, Hendrik, the next question's for you. And, we have different types of polyethylene, linear, low density. And within polypropylene, we have isotactic, syntactic, atactic, etc. Is there a difficulty with mixing those streams, say within polyethylene or low density polyethylene or within polystyrene?
I can't speak to polystyrene. I think the most prominent case for us is the
Polypropylene, I'm sorry.
Yeah. Also there, we don't do any particular sorting on the polypropylene. We do custom engineers of polypropylene. Again, goes mainly into durable applications. We are gonna look at sorting more of the packaging type of polypropylene out to going forward. But our most prominent case is, I think, the linear low and low density for our film customers. And there it starts with, knowing your feedstock. Is it coming from a distribution center, which is usually heavy and linear low density versus LD bag? So it starts there. It could continues through optical sortation. And then at the end of the day, there's also, the part that our lab plays to verify melt flows, densities, and so on. We can't usually hit 100% the spec of our customers, but we have a tight enough range. So we see every new customer request really as a separate project where we need to develop a resin specs that can fit for the application. But yeah, it's you will never hit it 100% with mechanical recycling, right? So we'll try to get as close as possible.
Jeff, the one question here is what level of monomer recovery is sufficient for commercializing the PET depolymerization?
I assume the question is what efficiency of recovery do you have to get to before it's economically viable? It's about 80%, and it's not just about the percent that you can recover, but it's also about the quality, right? You want very high quality, clear, materials that give you very high quality end products. And so for us, it's been as much about the quality as it has been the yield or efficiency, but we're at about 90% right now. And we think there's even some room to go above that.
Another question for you, when you depolymerize, obviously anything that's a dye or an additive or contaminant or label or whatever carpet backing there might be is left. What happens to that?
Yeah, interesting question. So, we have both mechanical and solvent-based processes for extracting that material. But what I didn't talk about is Eastman has a second recycling technology called carbon renewal technology. And essentially we can take those materials and gasify them to produce synthesis gas. And since the 70s, Eastman has actually been gasifying back then coal to make chemicals. And so we basically replaced our coal to chemicals process with a waste plastic chemicals process that produces methanol. That then goes into our acetyl stream and goes into our cellulosic materials, which is another part of Eastman's business. So a big part of what we're doing is trying to get those two recycling technologies to work together at scale.
That's an excellent solution. I appreciate that. Let's see. There are a number of questions that have come up both before and during about consumer education and public education and bringing these concepts even into schools. Can each of you speak about where that stands, what needs to be done, and really who should be doing it?
Well, I can tell you what we do here, and I'm very fortunate, and I realize that. We have a full-time education coordinator on staff. We also have an education endowment fund that in the event we ever reach our zero waste goal from our transfer station, that because we have a fee on each ton tip that goes to that we would still be able to educate their students. The local school district here has made it part of the curriculum, and every fifth grader comes here for a tour of our facility. And again, I realize we're really fortunate to have those funds. Not everyone has that. So yes, investment should be made. I would assume that investment should probably come at the state level, if at all possible. We are looking at legislation in Pennsylvania itself that would enhance the $2 tipping fee on every ton of trash to $5 for a recycling fund. But that has a variety of grants that are funded through that. So again, it's really hard to say what should be done. Every state is different. Every community is different. But agreed. It all starts with education, which is why I say something like TerraCycle, even if it might not fit my definition of recycling, it's raising awareness about your personal responsibility for your disposal.
I agree with that completely. I think education is so important, especially for students at the young level. I also really like the tools that we can use. There's different tools that are better for different generations and things like that. Something that's implemented at CCRA is Recycle Coach. And it's basically an app that you can go into and you can search, what should I do with this like clamshell fruit container? It'll say, oh, well, you can't put that in your curbside bin, but you can take it to these free drop-off bins.
And it is program specific to us. It's not just and that's where some of that nationwide confusion can come in.
So yeah, I think the big thing is having tools like that can be more program specific and target your specific community rather than this nationwide education, because everything's different and you can't have a blanket statement for recycling.
Andrew, back to a more technical question for you. Is obviously whenever you mechanically recycle a polymer, there's some degradation of mechanical properties. How do you work with that?
There's a couple of additives that can mitigate some of that, right? But we have to accept the fact that we're bringing this this plastic through another heat cycle, so it does degrade, and that's there's not much that we can do about it, right? On our end, given the process. So I know there was the idea is does this still go under the umbrella of circularity at the end of the day? I believe if this material is worked into packaging at 30 to 40%, then it still provides a benefit, right? How many times you can recycle it over and over again? I think right now we are somewhere between 6 and 7 cycles that material could probably do. But there might also be a scenario where at a certain point it's not fitted anymore for mechanical recycling, and then you go into a chemical recycling solution down the line. So I think those are things that still have to play out in the industry, where it's not 100% clear how such process could look like.
We've talked about some of these things, and can you speak about the critical success factors for collecting and sorting post-consumer recyclables? And maybe this is better for our front-end people, but elaborating on factors we can control for collecting and sorting.
I can touch on one piece of it. So we didn't originally plan on building 2 plants, right? We thought we could buy or source feedstocks that were going to be sufficiently homogeneous that we could run them through a pure chemical process. So one of the big learnings that we had is, these are just not, well-defined feedstocks, and you have to develop essentially a second, more highly refined mechanical sorting process before you run the chemical process. Now that may change, and distribution channels may change over time as people see more value in this kind of recycling. But for now, what we're really doing is tapping into to streams that exist already with fairly variable quality. And it was a big challenge. It was as big a challenge as the chemical part of our process.
Okay, I believe Michael hasn't given us the hook yet, but I think we're coming close to the end. So I'll ask if each of you have any last thoughts you want to share with our audience.
I just want to reiterate what I said. I think there's room for everyone at the table. I think Caitlin's generation and the works that these folks are doing is extraordinary, and we have to keep looking at solutions because the plastic streams are changing. It's not even plastic streams, it's packaging streams all over are changing. The emphasis on available funding is changing from the government. So we have to be creative and we have to work together. And it does mean that all the great scientists out there coming up with these solutions do need to take a step back sometimes and come and speak with people like us. Because at the end of the day, if they're making something that we can't collect and we can't send to a market to be processed, even if it is recyclable in a laboratory, it might not turn into a recycled material. So, but room for us all.
I'll follow up with that. I'm very lucky to be here. This has been awesome. And thank you all for coming to the webinar. My parting words would be, as I'm kind of starting to grasp more of the recycling world that there is out there, I think a big key thing is keeping conversation going and keeping work going. So something starting up a tailgate recycling program at your university that works for your university, I think is great. I worked as a tailgate ambassador going around telling people about how to recycle at Penn State football games, and just having those conversations about recycling with other people was one of the, I think, most beneficial things. And it helped to kind of, keep the education going because things are constantly changing. Things don't stay the same, especially in this industry. Everything fluctuates. So I think the main thing is to keep the conversation going and do whatever you can to help out.
Yeah, I think I would add what I had on one of my slides, that the consumer is driving everything, right? We as a consumer need to also embrace the look of recycled plastic. That's something that's happening with paper already for a long time. So that would really help push the industry. And again, recognizing that it's definitely not a material issue; it's a waste management issue with plastics that can be solved. And where the industry also needs to continue working on design for recycling to simplify it for everyone, including again the consumer, to make sure we can recycle in higher percentages.
Yeah, I don't have a lot to add. I agree with Mimi. There's so much to do here. There's so many challenges. There are engineering challenges, economic challenges, distribution challenges, material science challenges, and each one takes a different kind of solution. And we're seeing lots of exciting pieces, but we need lots of additional solutions before we really start to tackle fully the plastics challenge that we face, plastics waste challenge we face.
Thank you all. I've learned a lot and appreciate everything that you shared with us. Want to take a moment to just remind people that the Science History Institute, based in Philadelphia, if you're local to Philadelphia, it's easy to visit. And do want you to know that we do have a lot of virtual and online programs, including ones in partnership with the American Chemical Society. And so we reach people globally. So you don't have to be in Philadelphia to be a part of the Institute. And everything we do is free. So in order to do that, obviously, we need your support. So please go online and make a gift to the Institute, and that'll keep programs like this continuing. And this part is the Joseph Priestley Society. We have an index of all our recent programs on sciencehistory.org/JPS videos. That'll take you back to ones that we've done both with ACS and on our own over the last several years. The one in December was the chemistry of tea, which I think everyone will find fascinating. And we'd also like you to sign up for our next webinar in April 10th, which will also be co-produced with ACS on the use of CRISPR-Cas9 in therapeutics. So with that, I'll turn it over to Mike, and thank you all for attending.
Thank you for watching this presentation. ACS Webinars is provided as a service by the American Chemical Society as your professional source for live weekly discussions and presentations that connect you with subject matter experts and global thought leaders concerning today's relevant professional issues in the chemical sciences, management, and business.